Welcome back, sports fans, to another video from me, Spencer. Last time we had a really good discussion about LangChain and tool calling technology. If you haven't watched it, go and do that now. It's 15 minutes, but it's worth it because it'll explain some of the key concepts that we'll be discussing in this video. Last time we talked about task pattern and a crucial problem of memory. We understand from our last video that the problem of state management in an LLM is one that we can tackle in a number of ways. Last time we explored just passing a state from the front end and landing it in a monolithic prompt. And at some point you might remember I mentioned you wouldn't do this at scale. Well, here we're going to unpack a technology that allows you to solve the problems of memory and of state within agentic systems, and that is LangGraph. Last time we talked about LangChain. LangChain allows us to chain together runnables and agent calls and all this sort of stuff to make a system. LangGraph is slightly lower level, and it allows us to plan an agentic system's route through multiple agents. To get to grips with LangGraph, what we're going to do in this video is take our LangChain dice roller and we're going to rebuild it using LangGraph. The idea is really simple. The user types something, an LLM figures out what they want, and if we want them to roll dice, if they want to roll dice, we roll dice. If not, we politely decline. What makes this interesting is how we structure that decision as an explicit graph. So back to this discussion of state. You remember in our last iteration, which was a monolithic prompt, we had the expression of state as being cards shown, which we're passing from the front end. LangGraph works with nodes. Nodes are what we were discussing in the previous video. They're kind of like modularities. They're modular bits of code that can action things, they can make agent calls, they can execute runnables, and those form our nodes. We put those nodes in our graph, which is basically a formatted structure of how we want our flow to work. The first thing that LangGraph needs to work is a state definition. So you remember we talked about states in our previous video. We were handing the state cards shown from the front end in a really janky way. This is much the same, except very different. So LangGraph creates a typed dictionary that every single node in the graph can read to and write from, and this is called a state definition. Think of it like a shared blackboard that every node can kind of look at it, pick up what it needs, do its work, and then it's write its results back to it. The first node is the brains of the operation, and it's the determine input node. It takes the user's input and it asks an LLM to reason step by step using the scratchpad pattern that we discussed in the previous video, whether this is a dice rolling request. It gives the model explicit space to think before it commits to a structured answer, and this is good practice as we discussed in our previous video. Again, our scratchpad pattern doesn't force the model to behave a specific way, it elicits a specific response from it that we kind of want. Instead of asking the LLM, should I roll dice, yes or no, we give it a scratchpad block with guiding questions within it, which elicits chain of thought reasoning before the structured output, and that makes our classification more reliable. Remember in the previous video that we talked about structuring LLM outputs to get results that we want? Well, we're doing that here. We're passing the output in 3 lines. We've got number 1, should roll, number 2, number of dice, and number 3, reasoning. We pass this into a dictionary and we return it, and then LangGraph will take those keys and it will merge them into the shared state that we were discussing earlier. So remember we're talking about the blackboard? It's writing on the blackboard. There you go. Now this is where LangGraph really gets interesting. So back in the day, when we were mapping a conversation as part of traditional conversation design, we'd talk about conditionality and we'd talk about routing. This is something that we get out of LangGraph. So instead of giving a prompt and then going, well, and in this case do this, in this case do this, right? We separate functionality within our graph by giving nodes a specific path and then creating what we call conditional edges. So nodes have edges. You've got a node, you've got a node, you've got an edge, right? If a node has a conditional edge, we're basically saying, hey, under this condition, so if this output comes from this node, go this way through the graph, otherwise go this way through the graph. Pretty simple, right? So we're not just going to the next step in the chain, as it were. We're branching. We're saying, look at the state, return a string, tell the graph where to go next in the node. Pretty simple. Again, referring to the state, we're talking about that blackboard again. So what's going on is that we're saying add conditional edges, and we're taking 3 arguments. We're taking the source node, we're taking a routing function, and then we're taking a mapping from the return values to the destination nodes. If root intent returns roll dice, so we're getting that out of our initial node, then we go to the dice roll node. Otherwise, we go to the decline node. Easy. So this replaces the manual if-else routing that we had in our LangChain previously, which was pretty clunky and creates a monolithic prompt structure, which isn't desirable at scale because you can't really bulk it out. Instead of burying control flows in a function, which we did before, we're declaring it in the graph structure. Way more scalable, way easier to add functionality, and way easier to identify when things go wrong using LangSmith. So the next concept that we're going to talk about is our dice rolling node. You remember that in the previous node, we were passing an intent through. If that intent is roll dice, conditional edge routes us towards this node here. So this node calls our existing dice rolling functionality that we built last time to capture the output, then pass it through a second LLM call for a nice summary of what that was. Something interesting here is that we're using LangChain to have 2 tools in one node. So it's not necessarily like node is tool. It's not like that step-by-step functionality is split by tool. We can have 2 tools in one node to create a distinct sub-process. So number 1, we've got the sub-process call. We've got running second.py, which is in our Git structure, to generate a real random dice roll. And then number 2, we've got an LLM summary that hands that over using LangChain to string together summary prompt, LLM, and an output parser to get a neat summary of what's gone on to pass to the user. So we get more information than we got just out of the random dice roll. Next up, we have the decline node. So this is next up, we've got the decline node, and this is the next concept that we want to talk about. And this one's really, really simple. If the intent from the initial capture intent node is not roll a dice, then we just want to decline, and we want to give reasoning why we declined. We're not going to do anything else. There's no LLM call needed. We already have an explanation from the intent step. We can just pass that through here and decline that way. Now that we've declared our graph and defined our nodes and built them, we want to compile and run the graph. To do that, we compile the graph into a runnable app. Graph.compile validates the structure, checks all edges point to real nodes, so no nodes having an imaginary edge that it's not going to pass to, and then as an entry point, and then every path leads to an end. Then we invoke it just like we would any LangChain runnable, just like our second.py in our previous iteration, pass it in the initial state and get back the final state. So a bit more detail on code.invoke. It starts at the entry point that we declared in our graph. It runs the node, updates the state, so it goes and writes on that blackboard again, and then it evaluates the conditional edge. It goes, hang on a minute, right, based on what I've written on that blackboard and based on where I was on the blackboard, I should go this way. It then runs the next node, and it hits the end and returns the final state dictionary. From that final state, we pull a result and we pass that out to print an answer. So why use LangGraph at all? Well, number 1, explicit control flow. So we've got a graph structure that describes a distinct progression through the flow. We can look at nodes, we can look at edge definitions, and we can immediately see every possible path through the system. This is a really good opportunity for some solid design documentation. Now, in my experience, you don't want to go too into detail here because your data scientists and your team will have a really good idea of how they want to hand things through in a graph. What you can instead do is roughly sketch out in Miro or whatever tool you use how you would expect the agentic system to pass through. Make sure you list those conditional edges. This is another really good opportunity to flag hallucination risks, describe edge cases, describe error states. All of this is one big bundle that normally most conversation designers will be really familiar with. So it's a good collaborative opportunity. Number 2, we get that shared state. So what we were talking about before, you remember we said the state was an issue, that when you just make an LLM call and you hand a prompt and go, hey, if you've already done this, don't do this, it doesn't remember it. We're getting that out of this. That blackboard, key. Number 2, 3, extensibility. We discussed about this earlier. Let's say we don't want to just roll dice. We want to flip a coin as well. I love gambling. So I'm going to get sponsored by Rainbet or something. Rainbet, I want that money. I've got no ethics. Just hit me up. Please. It's hard out here. if we want to add a new capability, like flipping a coin, then we just add a node, and we add one more branch from our routing function. The existing nodes don't need to change, we just build that. So that's it. We took our initial dice roller and we gave it a proper structure with LANGGRAPH. Logic's the same. We've got intent detection, conditional routing, and then tool use, but now it's organized using a graph instead of just a chain of lambdas. Thank you for watching. See you next time. For relaxing times, make it Suntory times.